Okay, so it looks like not really anybody is showing up for the second review session. So instead, what I'm going to do is I'm going to put this little recording on Learning Suite, going through some example problems and talking about some of the concepts. I am going to talk mostly about the hard physics of the class, the mathematics, and some concepts in physics that we'll use throughout the course. And as well, as far as definitions and terms to know, you know where to find those things and look at those. If you have any questions, feel free to message one of us, the TAs. We can definitely help clarify anything that doesn't really make sense. But we're going to go ahead and get started on talking about some of the math side of things. I think at the very beginning of the class, we talked about units, right? And there's two things in particular we talked about units. We talked about things like metric prefixes, things like milliseconds or megawatts or kilojoules, things like that. And I can work through a problem. I'll just come up with one on how you would convert your units from these different metric systems. So for example, if I have let's say we have 12 megawatts, not mega, milliwatts, like that, right? And I want to convert that to just, we'll say we want to convert that to kilowatts, just for fun. And so what I would do is I would take a look, and this is on you're going to be on your test packet as well, is I'd look at my table and I see that, well, I can go, I have this milli here, and that tells me for every 1 milliwatt, I have 1 times 10 to the negative 3 watts, like that. And then from there, I don't want watts, I actually want kilowatts. So I'm going to move on from there and do this and say I want watts down here on the bottom. For every 1 watt, or actually for every kilowatt, 1 kilowatt, that's 1 times 10 to the third watts, like that. Then I just need to carry out my multiplication. And what that ends up being, if you see, this is 10 to the negative 3, just means we move the decimal over 3 spaces. So that ends up being 0.012 watts. And then to convert that to kilowatts, this is in the denominator. So again, I would move this over, this decimal place over 3 spaces. And that ends up being, there's 3 zeros then, in addition to my 0.0012. That ends up being 0.00012 kilowatts, like that. So that's just a basic review of SI units and the SI prefixes. Hopefully those make sense, and just feel free to let us know if you have any questions about that. But we're going to move on into the main thing that I think a lot of students have problems with, and that is with energy and power, especially with units where we talk about kilowatt hours or watt hours, the watt hour, right? And what is the watt hour? So the watt hour we define as, or how about this? Instead, we'll talk about the watt hour in just a second. Let's talk about the differences between energy and power. So energy is what makes things happen, sort of what allows motion, what allows things like heat and different interactions to happen, light, all that stuff is because of energy, right? It's not like matter. Matter is something that I can physically hold, for example, like my water bottle, physically holding that, and this is matter. But the motion, when I cause my water bottle to move or accelerate, that requires energy. It requires me to input energy and do some work, right? And we'll talk a little bit more about work and what that means in a second. But energy, we typically use in units of joules. In this class, we also use the kilowatt hour. We'll talk about a little bit more about what that means when we talk about power. We use joules, and sometimes we use British thermal units in this class, but it's not super important that you understand where that comes from or what exactly that means. Just know that we do sometimes use it, and you might be asked to convert from British thermal units to joules, or joules to British thermal units, so on and so forth. And then power, on the other hand, is just energy applied over time. So it's energy over time, right? It's a rate. It's the rate at which I expend energy, or the rate at which I create energy, things like that. And so the relationship, also, you can see that the relationship between power and energy is, if I take my power, whatever power I have, say I generate, I should talk about those units too. It's the units of power that we typically use are watts. You can use like British thermal units too, where it's British thermal units per hour. But this in general is what we use for to represent power, as we use the watt. And the watt is actually joules per second. That's 1 watt is equal to 1 joule per second. And you can see this is energy over time, right? And so the relationship between these two is, if I just say, if I have a power, say, of 10 watts, right? And I know that I apply that power over we'll say like 20 seconds, right? Say I have a power output of 10 watts for 20 seconds. The way I find the amount of energy is I take a look, or the amount of energy I expended in that time, is I take a look at this relationship here. The power equals energy over time. And I see that if I want to find my energy, I got to get this time over to the other side. And so I do that, and I do power, and I'll represent power with P and time with T, multiplied by time is equal to my energy, E. And that's the relationship that exists between them. Now we can talk about, finally, what are these kilowatt hours? Kilowatt hours are really, they can be kind of confusing because they have watts in them. So they make you think, oh, watts means power. But in this case, it's actually talking about energy. The definition of a kilowatt hour is the amount of energy I would use if, for 1 hour, my output, or my power that I'm spending or using, is 1 kilowatt. And so you can think of it, if we look at our kilowatt hour, it's a kilowatt is, so a kilowatt hour, a kilowatt is energy over time, right? It's 1 joule per second. And then our hour per time, right? Our hour, we're multiplying that by an hour right here, right? This is multiplied by an hour. And that's also a unit of time. So if I do another unit of time on top, then my units cancel here, and I end up with just an energy in kilowatt hours. And so that's why kilowatt hours are used a lot in industry, and talking about like power plants and how much power you use in your home and things like that. In physics itself, usually physicists like to stick with watts, but in this class, we'll definitely talk a lot about kilowatt hours, because we use kilowatt hours to talk about the consumption of energy, or the rate of consumption. Well, no, just the consumption of energy, and how much energy has been consumed over a period of time, given that we know their watts, or how many watts their power is. So if we look at, there's an example problem in our the midterm 1 example problems. We look at number 7 says my bill for electricity says I use 600 kilowatt hours this month, right? For 1 month. Now, the first part of that question asks how many joules of energy that is, right? So what we need to do is we say, okay, joules is energy. We need to look for energy. This is a unit of energy. So I just need to convert this into joules. The way I do that, they say this is 600 kilowatt hours, right? Or this is also, since a watt is equal to a joule per second, I can say this is 600 kilojoules per second. It's like kilojoule hours per second, which is that's a little weird, but we can work with that. We can work with our units, kilojoule hours per second, like this, right? Because I can substitute my joules per second in here, and that ends up being kilojoule hours per second. Now, I just want this joule part right here, right? So I need to somehow reduce this, make it so that this S is equal to that H. So I can actually get how much these seconds here on bottom is equal to the hour on top, so that I can cancel those out. So if I look here, 600 kilojoule hours per second. Well, I probably want to change this hour into seconds, right? So I'm going to put this hour down on bottom, so it cancels with the hour on top, and I'm going to put seconds here on top. Say, okay, how many? You could say there's, I suppose you could do it in minutes as well, and say that there's, in an hour there's 60 minutes, and then go from minutes, 1 minute to a second, like this. This works. What I normally do, though, is I just say, oh, 1 hour is 3,600 seconds, and that will cancel out as well. But for this problem, we'll use the 260 seconds here. And so I see my minutes cancel here with these minutes, and my hours cancel with this hour, and then these seconds cancel with these seconds, and I'm left with just kilojoules. And if I can run that through my calculator really quick, I get that my energy consumed is 216 and then 000, and that's kilojoules, right? And I'd have to use, it asks specifically for joules. So I imagine they want you to get rid of this prefix here. And the way I do that, again, I just put my 1 kilojoule on bottom and say there's 1,000 joules in 1 kilojoule, and then multiply that by 1,000, and I'd get my answer there. So it'd be 216, and then 3, and then a total of 6 zeros right here. So it's that's a 2. So my answer ends up being 216 million joules. And then the second part says, what is my average daily energy consumption? So we have to come back to this where it says it's 600 kilowatt hours a month, right? And it's asking for a average daily energy consumption, right? So there's a couple ways I can look at that. If I'm looking for the average, it's asking for the average amount of energy I use in a day, right? So if I know I use 600 kilowatt hours, and you could also use the joules here, but I'm not going to do that. I'm just going to give them what they gave me, and so, or use what they gave me, and then 1 month over 1 month. Well, I don't want it over 1 month. I want, however, what my average daily energy consumption is 1 day. So I do that by turning this 1 month into, we'll say 30 days is, And typically, I believe when they say, unless they specify otherwise, a month is 30 days. So that, and then I carry out my calculation. And do, since this is on bottom, I divide 600 divided by 30. Well, this month cancels that month. We do 0 cancel with that, and then 60 divided by 3 is just 20 kilowatt hours. And that's my average, and that's 20 kilowatt hours per day. That's what that means. Then this part here says, if my energy bill was $91, how much does it cost for 1 kilowatt of energy? Well, or kilowatt hour of energy, sorry. It says, well, then I look up here still and I say 600 kilowatt hours, and that costs this, right, is equal to hold on, how am I going to explain this? It's like, so if I used this much energy, right, then that means 600 kilowatt hours, that should be kilowatt hours times by the amount it costs for one. So it's some amount, some money amount that we don't know. I'll just put a dollar sign there, is equal to $91, like that, right? And in order to find this dollar amount, then I'd have to divide by 600, and that would give me by 600 hours. And we see this is dollars per kilowatt hour. So that's the unit it wants, right? Because it asks for how much energy does how much does it cost for 1 kilowatt hour of energy. So I want to figure out, well, for every 1 kilowatt hour of energy, how much does that cost? And so I just run that through my calculator, 91 divided by 600, and that gives me about 15 cents. So it's about 15 cents per kilowatt hour. Like that, and that would be my answer. Another common, or I guess it's one that we kind of did in the exercises, is they might ask, well, what was my average power consumption, right? What was my power consumption, basically, and or the rate at which I consume power or whatever, in watts. And so if I wanted to convert it to watts, I'd have to look at both. So it's 600 kilowatt hours over 1 month, right? And I'm actually going to write it like 600 kilowatt hours over 1 month, like this. And then when I look at this here, this is a power because it's energy over time, right? And I want a power. I want to end up with a power, except I want my power to be in kilowatts rather than kilowatt hours per month. And the way I do that is I see, well, I want just this part, these kilowatts right here. And so I need to somehow get rid of this hour, make this hour cancel out with this month. So I need to change this month into hours. And the way I do that is I just put a month on top here. Since it's on the bottom, it comes up to the top. 1 month over 30 days. And then 1 day for 24 hours. And then I see, or I guess I should just write H here, 24 hours, like this. And then I see that these days will cancel with these days, and this month cancel with this month, and then this hour finally cancels with that hour. And then I just run this through my calculator, 600 divided by 300, or sorry, divided by 30. So this is a days divided by 30 divided by 24. And that will give me my answer in watts. And I won't run through that calculation, but because we're going to move on to some other things. We're going to talk about now, we'll talk about work and what work means and where it comes from. So I think with the exercise question, there's a little bit of confusion on what work means. And so in physics, we define work to be the force times distance, more or less. And that distance or displacement has to be in the direction that this force is being applied, right? So in our exercises, we had an example where it was a girl carrying a box, right? And so on this box, while she's walking, so you could say, let's assume that after she picks up the box, she walks at a constant speed, right? So she doesn't accelerate at all. But once she picks up the box, she walks at a constant speed. So in that case, there's the force of gravity pushing down, and then there's also her pushing up on the box. And there's no motion happening in the up and down direction, right? There's no motion. The box isn't moving up and down. The box is moving this way, right? And so in the up and down direction, there is no work being done because this displacement is 0 in that direction. And so, and anything times 0 is 0, right? And technically speaking, since she's traveling at a constant velocity, she doesn't need to apply a force to get this to move. Though you could argue that she is, and that's okay as well. As long as she's applying a force and she's moving in that direction, she is doing work in this direction. But it's not really super important that. And then the next part I want to cover really is when she puts it on the ground and starts to push it, right? She puts it on the ground and then she starts to push it in a direction, right? And in this case, there is work being done, even if she were to be traveling at a constant velocity. If she's pushing the box at constant velocity, there is work being done because the force of friction is also pushing against her, right? And she has to push against that in order to get the box to move at all. And so the displacement is in this direction, and she's applying the force in this direction. So therefore work is being done. And then that is just more like a conceptual overview. You don't really need to know too much about the specifics of work and how that all what the definitions are and things like that. You won't really have problems that deal with work. You just need to, and like even this problem, it's a little iffy on where work is being done or not. You just need to understand that when we apply a force and whatever object is moving, if it's moving in the direction of the force, that means positive work is being done. But if it's moving perpendicular to the force, just like how in the box, right? In the box, you're applying force, or she was applying force upwards, but the box is moving this way. That means that there's no work being done in this direction, in the up and down direction, because there is no movement in that direction. It's just moving this way in the horizontal direction. But the other thing that we talked about is potential energy and work and how that relates, right? So using our definition here, right, the work done by gravity, or against gravity, I should say, is equal to, since force is equal to mass times acceleration, the work done against gravity is going to be equal to, since force is mass times acceleration, there's the mass of whatever object is being moved times the acceleration of gravity, and then times by the height, right? Because gravity is up and down. It doesn't move, left and right. So when we talk about work, we're talking about this. So if there's an example problem, actually, I'll go through briefly. Number Let's see if I can find it. I think there's a couple even, or we'll talk about work kinetic energy theorem in a second, but we have number 6 here. It says how much work is required for a 68 kilogram person to climb up 5 flights of stairs, approximately 18 meters. I assume it's supposed to say 18 meters tall. So if I look at that, I'm looking at this person here, right? And they're moving against the force of gravity. So they're doing work against the force of gravity. And that work is equal to the force times by the displacement. So in order to do that, we just look at this and say, well, it has to be, since the force is mass times acceleration, it's going to be the mass of the person times by the acceleration of gravity. And so when I put that all together, and the acceleration of gravity, g is equal to 9.8 meters per second squared when we're close to the surface of the Earth. So if I plug all that in, I just do 68 times, and usually I like to write my units so that things make sense. So 68 kilograms times by 9.8 meters per second squared times by 18 meters. And I see, like, for example, you don't really need to know this, but joules is actually equal to a kilogram meter squared per second squared. You don't need to know that, but it helps me in this problem because I see I have a meter here and a meter here. So that means I have meters squared, and then I have seconds squared on the bottom, and then I have kilograms. And so that means this is a joule. And I should expect my answer to be in joules since work is being done, and that has to do with energy. And if I run that through my calculator, 68 times 9.8 times 18, that's 11,995.2 joules. And that's how much work is done by that person when they climb up the stairs 18 meters. How much work is being done against gravity? Because as we were talking about earlier, there's other types of work that can be done. But in this case, we're just talking about work against gravity. And that's usually what we'll talk about here in this exam, at least at this part in the class. And so I think the other big part about work is what's called the work kinetic energy theorem. So what that says is the work done on something is equal to the change in kinetic energy. That's what the work kinetic energy theorem says. So, and why does that make sense? Well, we say kinetic energy can be written as the kinetic energy of an object can be written as 1/2 the mass of the object times its velocity squared, right? So if the kinetic energy changes, that means I accelerate. And in order for there to be a change in acceleration, there has to be some kind of force. And since we're moving, that means that force has to be applied over a distance somehow, meaning their work has to be done, right? Because work is force times distance, right? And you don't really need to understand all the intricate parts about that. You just need to, I just explained that. So maybe it'll help you understand where this comes from or why this makes sense. But we're just going to talk about how the work equals the change in kinetic energy. This triangle is a delta. It's delta, the Greek letter delta, and it means change in. We use it in mathematics and in physics to mean the change in something. And so what this really is saying is that if I want to calculate the work, I just have to take the change in kinetic energy is going to be equal to my initial, or is going to be equal to my final kinetic energy So we'll just say K. So my final kinetic energy minus my initial kinetic energy. Or in other words, it's going to be equal to 1/2 the mass. And since the mass will not change in our problems, it's going to be 1/2 the mass times the velocity final squared minus 1/2 that same mass times the initial velocity squared, like that. And that is what we're going to use to solve these kind of problems. There's a problem. There's a couple problems here. We'll start with number 2. So number 2 says how much work is done by the brakes of a 100 kilogram scooter. Write that down. As it slows down, or yeah, as it slows from 18 meters per second to a stop, right? So if I look at my work kinetic energy theorem, I have a mass, I have an initial velocity, and what's my final velocity? Well, it says it comes to a stop, so therefore my final velocity has to be the 0. It has to be 0 meters, or just 0 meters per second, or just 0, right? So if I plug that into my equation here, get work equals my final velocity, which is 0. So it's 0. And I shouldn't have to plug that in, because if I do 0 squared times m times 1/2, it's just going to be 0 minus, and then we plug in 1/2 m, and then 8, or I guess I should plug in numbers, huh? 1/2 times 100 kilograms times 18 meters per second squared, like that. So I plug that in my calculator. I get 16,200 joules. And that's a negative 16,000, right? There's a minus sign up here. I get that. And now, does that answer make sense? Yeah, because the brakes, if we think about, if the scooter, say this is the scooter, I know it's wonderful drawing. If the scooter is moving this way with an initial velocity, right? The initial velocity of 18 meters per second. If it's moving this way, and so my motion is in this direction, but the force that the brakes are applying is in the opposite direction. So therefore, since the force is opposite, my work being done should be negative, since it's opposite to the direction of motion. Hopefully that makes sense. And we can look at, let me see, I don't think there is another problem like that in here, but that's okay. There is one, there's sort of a trick problem. Number 8 says a Formula 1 race car can have a 1050 horsepower engine. How much energy is used to accelerate from 0 to 60 miles per hour, or 27 meters per second, right? In 2.6 seconds. Now, this is kind of a trick question because it gives you some extra information that you don't need, right? It gives you the speed, right? And that makes you think, oh, work kinetic energy theorem, that's what I need to use. But actually, we're given a power, which is an energy over time, right? Is equal to power, right? So all I need to do to find the energy that I used is multiply by time, my time by my power. And so in this case, and you'd have to convert your horsepower to something you can actually use, like watts, right? You'd have to convert that to watts, because horsepower, we use SI units, so I would convert it to watts. And so to do that first, I do 1050. Then in my book, and the table in the book tells me that for 1 horsepower, I have 746 watts, 746 watts, like that. So I'd have to convert that to get an answer. And then now that I have my energy in watts, I can multiply by my time, because power times time equals energy, to get my total energy flow. And I won't go through the whole calculation with that. Just wanted to bring that up, because sometimes you might see a question that's trying to trick you into using the work kinetic energy theorem when that's not actually what you need to use to solve the problem. So let's see what is next. Oh, I guess there is another problem that uses the work kinetic energy theorem. Oh, it's part 2 that's in question, actually. The part B that's in question. I didn't realize that. And there is a video. Actually, I won't go through that part. There's a video solution on Learning Suite, so I won't go through that part. But if you have questions about it, please let me know. Now let's see. We did work kinetic energy, and then the other thing we talked about is calorimetry or thermodynamics, right? So there's a couple things with thermodynamics, and we talk about specific heat and heat capacity, and then also the heat, which I know I think in your book it's H, so I'll use H. But typically, if you were to ever see an equation that says Q equals that, a lot of times in physics we use Q to mean heat as well. So heat equals, it's the mass times the specific heat of whatever that object or whatever mass you're analyzing is, times by the difference in temperature, right? And for these, you typically want to be in kelvins, though if you're given a difference in temperature, Celsius will work as well. And I won't go into why, but you can use Celsius or kelvins as long as both your final and initial temperature are in Celsius, or both of them are in kelvins. So I should probably also talk a little bit about what the difference is between heat capacity and specific heat. So heat capacity deals with how much it costs, or how much heat capacity. I don't know how to spell capacity, apparently. Capacity. Heat capacity deals with just if we have a body of something. For example, if we have a body of water, right, that's like 12 kilograms or something like that, right? The heat capacity of that body of water, of this whole body of water, is how much heat I need to add in order to raise this whole body of water by to raise the temperature of this whole body of water by 1 degree, right? That's what heat capacity means. Specific heat, though, is how much heat I need. Specific heat is how much heat I need in order to raise 1 kilogram, exactly 1 kilogram of this substance 1 degree, right? And so the heat capacity of a body can increase if we add more substance to it, right? So for example, the heat capacity of 12 kilograms of water is higher than the heat capacity of 5 kilograms of water, because there's more water, so I have to use more heat to heat the whole thing up. And that's the main difference. Meanwhile, the specific heat is only talking about 1 kilogram of the substance, right? So for example, and I mean, I can't think of certain, I guess heat, for example, the specific heat of water versus the specific heat of ice, right? The specific heat of water is much higher than the specific heat of ice. Even though we have 1 kilogram of water and 1 kilogram of ice, the specific heat of water is much higher. And so that's the main difference. And hopefully that helps. I know there's a lot of people got confused. Even I got confused when I first learned about the difference between these two. And so hopefully that helps. But now we go back to our calorimetry equations, as we have the heat this is the heat that we need in order to change the temperature of an object, right? If we're given an object, say we're given water, right? Or we're given an ice cube, right? If we want to figure out how much heat it takes to heat the water up or heat the ice up 1 degree, we would use this equation right here. But if I want to figure out how much heat it takes for an ice cube to melt into water, I would use this equation right here. And this is the equation for latent heat. And so usually I should probably look what it is exactly in the book, what equation it gives you, or even I guess on the test packet. Let me see, because in physics, it might be a little different. It does use L. Okay. So I'll use L for latent heat. And so this equation is the mass times the latent heat. And it depends on whether it's going from a solid to a liquid or a liquid to a gas or vice versa, right? And so if your L depends on if it's going from a solid to a liquid, then you use the latent heat of melting or the latent heat of fusion. But if it's going to a gas or it's a gas going to a liquid, we use the latent heat of, I suppose, condensation or the latent heat of vaporization is what that's called. And those are values that are measured, and you'll find in your book, just like the specific heat, they're very similar to what specific heat is. And so there was a problem. We'll go through an example problem. A couple example problems. And so this one, it says, number 3 says how much energy is needed to heat a 0.3 kilogram vase from room temperature. Or actually, that one has a video solution, so I'm not going to do that one. But it says how much energy is needed to melt 2.26 kilograms of ice if it has been stored at negative 18 degrees Celsius. So this one is also kind of a trick question. So let me bring up. So something we didn't really talk about, but is important in calorimetry and thermodynamics is melting points and boiling points and things like that, right? So, and freezing points, right? And so the freezing point of ice is 0 degrees Celsius, right? And so that's also the point at which it'll start to melt, when ice will start to melt, is at that point, right? So this problem tells me that I start with an initial temperature of negative 18 degrees Celsius, right? So that means if it heats up a little bit, it's going to heat up, but it's not going to melt. And so we need to calculate first how long, and this is similar to the problem we had in the exercises with the chocolate being left in the car, if you remember that. This problem is going to be just is how much energy is needed to melt. This problem, we need to figure out first how much energy it needs to get to just 0 degrees Celsius. And after it reaches 0 degrees Celsius, how long does it take for it to melt? Or not how long, but how much heat it takes for it to actually melt, right? The latent heat of melting. We need to figure that out first. So in order for a temperature change, I need to use this equation. H equals heat equals the mass times the specific heat times by the change in temperature, right? So in this case, my change in temperature is going to be, my final temperature is going to be 0 degrees Celsius, and my initial temperature is negative 18 minus negative 18 degrees Celsius, like that. That's my change in temperature. Then my mass, I didn't write that down. I think it's 2.26 kilograms. I need to write that down. 2.26 kilograms, like that, right? So my mass is equal to that. And then the specific heat for ice is, and I'm going to need the latent heat as well. So I'll write that down, latent heat. The latent heat specifically of melting, or of melting or of fusion. Both are the same. Let's see. Do I have Okay, yeah, specific heat of common elements, or as ice is 2050. So it's 2050, and the units, don't worry too much about units on these. Joules per kilogram, then Celsius, degrees Celsius. And then the other one is latent heat, the latent heat of fusion in this case is 334 kilograms, or I think it's kilojoules. Whoops, kilojoules per kilogram. That's what it is. Kilojoules per kilogram, right? So we'll use that later, but for now, we're just worried about this because we're working with this equation. So if I write that in, and my total heat is going to be equal to the heat it takes to warm up the ice and the heat it takes to the latent heat of fusion that comes from melting. So the heat it takes to melt the ice, right? So my HW, the heat it takes to warm up, is going to be my mass times my specific heat times delta T, which is going to be, my mass is 2.26 kilograms. And my specific, my specific heat is 2050 joules per kilogram Celsius degrees. And these are found in your book and your test packet. And this last part is my difference in temperature, which we found up here, and that's just going to be 18 degrees Celsius. And I've been writing it backwards, but that's okay. So then that's just my latent heat, or not my latent heat, my heat I need to warm it up. Now I need the heat it actually takes to melt it, which is actually, since it's melting, it's changing phases, it's going to be the latent heat equation, where this is the latent heat of fusion. So that would be 2.26 kilograms times by latent heat of fusion, which ends up being 334. Should write a subscript there, 334 kilojoules per kilogram. And now, let me make sure something really quick. I think I might have forgot. Oh no, this is just joules. Okay. So that's going to change my answer a little bit. If I see my units, I need to be careful of my units, right? So this will give me, these will cancel, give me kilojoules. These will cancel. I should be specific and say that this is on bottom. This is joules per kilogram degrees Celsius. So like this is in the denominator right here. So these will cancel. Then these kilograms will cancel. I'm left with joules, but these are kilojoules, and I can't add those two things together. So if I want to change these to kilojoules, or what does the question say specifically, I guess? The question says, it just says how much energy. So I'm going to use kilojoules. So I need to convert that to kilojoules by saying it 1 joule, or I should do 1000 joules is equal to 1 kilojoules, right? And then those joules will cancel, and I am left with kilojoules on top. So I make sure when I add these together, they're the same unit, that's kilojoules, and this will be in kilojoules when I finish up. So I just need to find whatever these answers are and add them together. When I do that, I get, let's see, 2.26 times 2, I'm just going to do times by 18. divided by 1,000 gives me 83.4 or 83. Yeah, 83.4. I'm rounding. Kilojoules plus, so that's from this part right here, and I got that from here. Then plus my other, the heat of melting, which ends up being 334 times 2.26 kilojoules, which is 754.8 kilojoules, and I add those together. Oh, whoops. 83.4. I get 838.24 approximately kilojoules. And that ends up being, or I guess not that, it would just be 0.2 kilojoules. And that would be my answer for that question. Right. So there's that main thing. That's the main idea behind what's called calorimetry, and it's a little bit of what we get from thermodynamics. The other part of thermodynamics that we talked about, we did talk about the different ways that heat travels, and we used some formulas for that, but I don't believe that will be on the test. And so I wouldn't worry too much about it. Just know that there are different types. There's conduction, convection, and radiation, and those are the different ways that heat can be transferred. And so then the other part of thermodynamics that we talked about is efficiency. And with a heat engine, we have an efficiency, right? So what the idea behind the heat engine is that when we like burn coal, we know how much energy it produces. The only problem is we can't efficiently use all of that energy. Some of it gets lost and goes somewhere else, right? So efficiency tells us, well, how much energy going in actually comes out into energy or is used as energy that we can use, like that is used for other things, right? It's like how much energy actually turns into work that we can use on for different purposes, right? So the equation for that one, and this is in your to find the maximum efficiency possible given a heat engine is just, or given a system of some kind, is just E limit efficiency. The limit of the efficiency is equal to 1 minus the hot temperature over the cold temperature. And this one, again, it doesn't really matter about the units as long as they're the same. And in Celsius or Kelvin, preferably, though I suppose I would probably do Kelvin, because if you get a negative, actually for this one, you will have to use Kelvin now that I think about it. So you use Kelvin for this one. And this will tell us how efficient our engine is, or our system is, in converting energy into work. So number 5 in the example problems is: an ideal closed cycle gas turbine engine operates between the peak temperature of 1727 degrees Celsius and an output temperature of 27 degrees Celsius. What is the maximum thermal efficiency of this engine? So like I said before, we're going to have to convert it into Kelvin. So in order to do that, I take my temperature hot, so the bigger of the two temperatures is equal to 1727 degrees Celsius. And in order to change that into Kelvin, I have to add 273, right? It's 273 point something. I always forget what that is. It's not super important. I think it's 273.15 is what it is. So to change this to Kelvin, I just add 1727 plus 273.15. And this 0.15 ultimately won't matter, but I'll do it for the sake of being careful. 273.15. That gives me 2000.15 Kelvin. So that's my hot temperature, and then my cold temperature. given to me was 27 degrees Celsius. So 273.15 plus, and I think, let me see what it says in here. Because if it just says 273 in your test booklet, so I'm just going to use that actually. So this 0.15 would go away. And this would just be 273 plus 27 is just going to be 300 equals 300 degrees Kelvin, or just 300 Kelvin, not degrees Kelvin. So now I have my temperature hot and my temperature cold, and then I just plug it into my equation. I say the efficiency, the limit of the efficiency is equal to 1 minus a hot temperature over the cold temperature. And this number is unitless. It's a ratio, so we don't worry about that. Units on that, and even if we did, the units would cancel here, right? So 1 minus, and then if I put that in my calculator, 2000 divided by 300 will give us an efficiency of 0. Wait, maybe I did something wrong. Hold on. Did I look at the equation wrong? Oh, I did. I wrote it down wrong. It is not hot over cold. It's cold over hot. It's 1 minus T cold over T hot. So the cold temperature over the hot temperature. So this is actually flipped upside down. This is 300. That makes more sense. I was a little confused there. 2000 Kelvin. So 1 minus, and that's going to be 300 over 2000. It's going to give me an answer of 0.85 efficiency, which is a pretty high efficiency. 0.85. Or you could say that my engine is 85% efficient. So there's that. And we talked a little bit, there's a little bit about percentages. I'm not really going to go over that. There is an example problem in number 1 that talks about that. And it talks about how much energy is used in one day and how much coal, things like that. Those are just conversion problems. Like you have some initial heat, or not, some initial energy, say like 1000 megajoules, right? And you need to figure out, well, how much coal does it cost to make that? Well, in your book, it tells you that a coal, a kilogram, or it gives you a rate, if I can find it. Let's see, I think it's table 3.3. It says that coal is 43 megajoules per kilogram. So if I want to change this to kilograms, I put megajoules here on the bottom. Kilograms on top. And I know that there's 43 megajoules for every 1 kilogram of coal. So these megajoules will cancel. I just do 1000 divided by 43. And that gives me how much coal I need, how many kilograms of coal I need to burn or to use in order to generate 1000 megajoules of energy, 23.3 kilogram of coal. So there's that. That was the other thing. And then there's like stuff about percentages, which we won't talk about. There are some example problems on there. If you need some help, just let me know. And yeah, that is about it. I think I'll call it for then. Good luck on your midterm. If you have any other questions, feel free to Slack me or send me an email or send me a message on Learning Suite. I will warn you, though, on Learning Suite, I do not check that as often as I do everything else. So good luck. And yeah, we're here if you need any help. And I hope you enjoy conference this weekend.